Greetings, cosmic explorers. Settle in, find your peace, and allow the universe to unfold around you. Tonight, we embark on a profound journey, delving into one of the most audacious challenges to our fundamental understanding of gravity and the cosmos itself. For decades, the invisible hand of dark matter has been the reigning explanation for the universe's most perplexing mysteries. But what if the answer wasn't hidden matter, but a subtle whisper in the very laws of physics? What if Isaac Newton, brilliant as he was, only saw part of the picture? We're about to explore Modified Newtonian Dynamics, or MOND, a theory that dares to rewrite the cosmic rulebook. So, dim the lights, perhaps grab a warm drink, and prepare to ponder the fabric of reality. If you find yourself enjoying this journey, a quiet like or share truly helps spread the wonder. Now, let us begin our deep dive into the gravitational enigma. From the deepest canyons of the ocean to the furthest reaches of the cosmos, our journey through science often presents us with profound and captivating mysteries. Today, we turn our gaze to one of the most persistent and enigmatic riddles of the universe, the cosmic missing mass. For decades, astronomers and physicists have grappled with a perplexing discrepancy. The universe, by all accounts of its gravitational behavior, seems to contain far more mass than we can actually observe. This unseen presence, this phantom gravitational architect, is what we've come to call dark matter. But what if the problem isn't with the matter we can't see, but with the rules by which we calculate its influence? What if our fundamental understanding of gravity, honed over centuries by giants like Isaac Newton, needs a subtle, yet profound, adjustment when stretched across the truly vast scales of galaxies? This is the radical proposition at the heart of Modified Newtonian Dynamics, or MOND. Imagine the grand, majestic spiral of a galaxy, its countless stars and gas clouds swirling in a cosmic dance. According to Newton's laws of gravity, the stars further from the galactic center, where the visible mass thins out, should slow down, much like planets further from the sun orbit at a slower pace. Yet, when we actually measure these velocities, particularly in the outer regions of galaxies, we find something entirely unexpected. The stars are moving too fast. Their rotation curves, instead of declining, remain stubbornly flat, almost as if there's a massive, invisible halo of something holding them in orbit. This observation, first systematically highlighted by the pioneering work of Vera Rubin and her collaborators in the 1960s and 70s, isn't just a minor anomaly. It's a colossal problem, a cosmic riddle that challenges our most cherished physical theories. It's what we call the missing mass problem. Before Rubin, even earlier studies like Fritz Zwicky's analysis of the Coma cluster in 1933 and Horace Babcock's work on Andromeda in 1939 hinted at this unseen gravitational heft. There are essentially two primary paths to resolve this dilemma. The first, and most widely accepted, is the dark matter hypothesis. This postulates that the universe is indeed brimming with an invisible, non-baryonic substance, dark matter, that interacts with normal matter only through gravity. It's a fundamental component of the universe, forming vast, unseen halos around galaxies, providing the extra gravitational pull needed to explain those flat rotation curves. The second path, less trodden but equally compelling, leads us to MOND. This theory, first proposed in 1982 by the Israeli physicist Mordechai Milgrom, suggests a fundamentally different solution. Milgrom posited that perhaps, just perhaps, Newton's law of gravity itself needs modification. Not in the strong gravitational fields we experience here on Earth or within our solar system, where Newton's laws have been exquisitely tested, but in the extremely weak gravitational fields that prevail in the outer reaches of galaxies. Think of it this way. Our experiments on Earth, our space probes exploring the solar system, all operate under relatively high accelerations. The forces are strong, and Newton's elegant equations work perfectly. But what happens when accelerations become minuscule, almost imperceptible? Milgrom suggested that below a certain critical acceleration value, which he denoted as a sub, the gravitational force might not decay as rapidly as Newton's inverse square law predicts. Instead, it might fall off more slowly, providing that extra gravitational tug without needing any invisible dark matter. This critical acceleration, a sub, is a new fundamental constant in Milgrom's framework, marking the transition between the familiar Newtonian regime and the deep MOND regime. Its value, when fitted to galactic rotation curves, is remarkably small, approximately 1.2x 10^-10 meters per second squared. To put that into perspective, it's about 100 billion times weaker than the acceleration due to Earth's gravity. It's an acceleration so subtle, so gentle, that it has no noticeable effect on the dynamics of our solar system, where accelerations are far greater. But in the vast, sparse outer regions of a galaxy, it becomes profoundly significant. Milgrom's law, at its core, isn't a complete theory of gravity in the same vein as general relativity. Instead, it's an empirically driven modification to a classical equation. Much like Kepler's laws described planetary motion before Newton provided the underlying gravitational framework. To make MOND a truly coherent and self-contained physical theory, satisfying fundamental principles like conservation laws, it needs to be incorporated into a more complete hypothesis. Over the years, various theoretical frameworks have emerged to flesh out MOND. One interpretation views it as a modification to Newton's second law, suggesting that force isn't simply proportional to acceleration, but rather to a modified version of it. However, this modified inertia interpretation has faced significant challenges from laboratory experiments here on Earth. The more popular and extensively explored interpretation casts MOND as a modified gravity theory. Here, it's the universal law of gravitation itself that gets tweaked. Imagine the gravitational force between two objects being modified by an interpolating function, a mathematical bridge that smoothly connects the Newtonian behavior at high accelerations to the MOND behavior at low accelerations. This function, while not uniquely specified by the initial hypothesis, ensures that in the deep MOND regime, the gravitational field increases with the square root of mass and decreases linearly with distance, rather than the inverse square. Two notable classical field theories have emerged from this modified gravity perspective: AQUL and QMOND. AQUL, or a quadratic Lagrangian, was first constructed by Milgrom and Jacob Bekenstein in 1984. It modifies the gravitational term in the classical Lagrangian, leading to a nonlinear generalization of the Newton-Poisson equation. This framework is particularly useful for understanding how the MOND gravitational field arises from a given distribution of visible matter. More recently, QMOND, or the quasi-linear formulation of MOND, has gained prominence. Developed in 2010, QMOND introduces a distinction between the true MOND acceleration field and the Newtonian acceleration field. It's often preferred for its computational friendliness and intuitive approach, allowing researchers to calculate the distribution of phantom dark matter that would be inferred if one were to analyze a MOND system using purely Newtonian physics. Intriguingly, AQUL and QMOND can be derived from each other using a mathematical transformation, suggesting a deep underlying connection between these different formulations. One of the most profound and unique predictions of MOND, arising directly from its nonlinear nature, is the external field effect, or EFE. In Newtonian mechanics, a small system, like our solar system, can be effectively decoupled from the larger galactic environment. The gravitational influence of the galaxy doesn't, in principle, alter the internal dynamics of our planetary orbits. But in MOND, because the modifications to gravity depend on the total acceleration, not just the acceleration due to local sources, the internal dynamics of a system can be subtly influenced by external gravitational fields. This means that a subsystem, even if its internal accelerations are below the critical value, a sub, might behave in a Newtonian manner if it's embedded within a stronger external gravitational field. Conversely, if both the internal and external fields are below a sub, The system's dynamics would be MOND, but with an effective gravitational constant that is subtly enhanced. This breaks with the strong equivalence principle, a cornerstone of general relativity, though it respects the weak equivalence principle. The external field effect isn't just a theoretical curiosity. Milgrom himself postulated it in his early papers to explain why some open star clusters, despite having low internal accelerations, didn't show mass discrepancies. It's now recognized as a crucial element of the MOND paradigm and has even garnered some observational support. For example, recent analyses of the Spitzer photometry and accurate rotation curves, or SPARC, sample, combined with estimates of large-scale external gravitational fields, have shown evidence consistent with the EFE in weak gravitational fields around rotationally supported galaxies. This is a significant finding, as such an effect is not predicted by the lambda-CDM model, the standard cosmological model that relies on dark matter. In essence, MOND offers a fundamentally different lens through which to view the universe's missing mass problem. Instead of inventing a new, unseen component of the cosmos, it proposes a refinement to the very laws that govern its interactions. This idea, while challenging deeply ingrained scientific paradigms, has a compelling elegance. What if the universe, in its grand design, operates by slightly different rules at its most expansive and most tenuous frontiers? This initial, audacious premise sets the stage for a scientific debate that continues to reverberate through astrophysics and cosmology, a debate we will continue to explore in the segments to come. We continue our journey through the cosmic riddle of the universe's missing mass, turning now to a truly audacious proposal: Modified Newtonian Dynamics, or MOND. Imagine a scientist observing the universe, deeply familiar with the elegance and power of Newton's laws, yet also keenly aware of their limitations when applied to the grand scale of galaxies. This was the position of Israeli physicist Mordechai Milgrom in the early 1980s. He looked at the perplexing rotation curves of galaxies, the very observations that hinted at vast quantities of unseen dark matter, and dared to ask a different question. What if gravity itself, or even inertia, behaves differently at extremely low accelerations, the kind found in the sprawling outer reaches of galaxies? Milgrom's insight, first presented in 1983, was a radical departure from the prevailing consensus. He proposed that the gravitational force experienced by a star in the outer halo of a galaxy doesn't decay as quickly as Newton's inverse square law would predict. Instead, at accelerations far weaker than those we encounter in our everyday lives, or even within our own solar system, the rules of gravity might subtly shift. This isn't about adding an invisible substance, but about revising the fundamental laws that govern how mass interacts. At its core, MOND posits a critical acceleration scale, denoted as a naught a. When accelerations are much larger than a, as they are in our solar system, MOND essentially reverts to Newtonian gravity. The dynamics remain intact. Our planets orbit the Sun precisely as Newton described. But when accelerations drop below this critical threshold, into the extremely tenuous gravitational fields found in the outer fringes of galaxies, MOND predicts a departure. The gravitational pull, rather than weakening by the square of the distance, might only weaken linearly with distance, or even as the square root of the mass, instead of being directly proportional. This subtle but profound alteration could, in theory, explain the flat rotation curves of galaxies without the need for vast, unseen halos of dark matter. Consider the implications of this. If Newton's laws are not entirely universal, if they have an Achilles heel at extremely low accelerations, then our understanding of gravity, a force we've studied for centuries, would need a fundamental recalibration. This isn't just a tweak, it's a philosophical shift. Instead of explaining away the discrepancy with an invisible component, MOND suggests we've misunderstood the very fabric of space-time's interaction with mass at certain scales. Milgrom's initial formulation wasn't a complete, self-contained theory. Rather, it was an empirically motivated modification, akin to Kepler's laws, offering a description without fully explaining the underlying mechanism. To transform it into a robust physical framework, scientists had to explore two main interpretations: modified gravity or modified inertia. The modified inertia perspective suggests that it's Newton's second law, the one stating that force equals mass times acceleration, which needs adjusting at low accelerations. In this view, an object's resistance to change in motion, its inertia, isn't simply a constant value, but rather depends on the magnitude of the acceleration itself. However, this interpretation has faced significant challenges from laboratory experiments, which haven't detected such deviations even at very low accelerations. Far more attention has been given to the modified gravity interpretation. Here, Milgrom's law is seen as a change to Newton's universal law of gravitation. The force of gravity itself is altered at low accelerations. This approach has led to the development of more complete MOND field theories, such as Ackwell and Cumond, which attempt to embed Milgrom's empirically derived law into a consistent theoretical framework that respects conservation laws. These theories, through complex mathematical formulations involving nonlinear generalizations of the Newton-Poisson equation, aim to provide a unique and consistent description of how objects move under these modified gravitational rules. A crucial, almost poetic consequence of MOND is what's known as the external field effect, or EFE. In Newtonian mechanics, the internal dynamics of a system, like the orbits of stars within a galaxy, are largely independent of the larger gravitational field it's embedded in. You can effectively decouple the system, but because MOND's laws are nonlinear, this decoupling isn't possible. The internal motions of a MOND system can be influenced by the gravitational field of its surroundings, even the entire universe. This effect, predicted by Milgrom in his early papers, has been identified as a unique fingerprint of MOND. For example, some open star clusters, whose internal accelerations would normally fall into the deep MOND regime and thus show a mass discrepancy, are observed not to. The EFE offers an explanation. If the cluster is under the influence of a strong enough external galactic field, it effectively pulls the cluster back into a Newtonian-like regime, masking the MONDian effects that would otherwise be apparent. This subtle interplay between local and global gravitational influences is deeply reminiscent of Mach's principle, suggesting a profound connection between local dynamics and the universe at large, a connection that MOND may be the first to concretely demonstrate. The value of this critical acceleration constant has been empirically determined by fitting MOND's predictions to observed galaxy rotation curves. It's found to be approximately 1.2x 10 superscript 1 meters per second squared, a value that has remained remarkably consistent across numerous studies. This seemingly arbitrary number also bears an intriguing resemblance to fundamental cosmic constants, such as the product of the speed of light and the Hubble constant, or even related to the cosmological constant itself. Whether this is a mere coincidence or a hint at a deeper connection between galaxy-scale dynamics and the universe's expansion remains one of the most fascinating questions for MOND proponents. While MOND's initial goal was to explain galaxy rotation curves, its proponents argue that its elegance extends to a wider range of astrophysical phenomena. Unlike dark matter, which requires a hypothetical, invisible substance with specific properties, MOND offers a single, universal modification to gravity that, they claim, neatly accounts for observed patterns without additional assumptions. For instance, MOND predicts a specific relationship between a galaxy's baryonic mass, the visible stars and gas, and its asymptotic rotation velocity. This prediction, known as the mass-asymptotic speed relation, or its observational counterpart, the baryonic Tully-Fisher relation, is found to be in remarkable agreement with observations, a success that dark matter models often struggle to replicate without fine-tuning their halo properties. Furthermore, MOND inherently predicts a strong correlation between the visible mass distribution within a galaxy and its rotation curve. If you see a bump in the light, you should see a corresponding bump in the rotation. This is often called Renzo's rule, and it's a direct consequence of MOND's emphasis on baryonic matter as the primary gravitational driver. In contrast, in dark matter models, the dominant dark matter halo is often assumed not to perfectly track the baryonic matter, making this tight correlation less straightforward to explain. Even more striking is the mass discrepancy acceleration relation, which connects the amount of missing mass inferred by Newtonian analysis to the acceleration experienced by stars within a galaxy. MOND predicts that this inferred dark matter effectively vanishes when accelerations exceed a. For dark matter models, explaining why an invisible substance should disappear or become irrelevant above a certain acceleration threshold is a significant challenge. The success of MOND isn't limited to spiral galaxies. Observations of massive elliptical galaxies, which are thought to be in the Newtonian regime for most of their baryonic mass, show their rotation curves falling off as expected by Kepler's laws. This is in stark contrast to the prediction of dark matter halos, which would imply a constant asymptotic velocity. MOND effortlessly explains this observation. Beyond individual galaxies, MOND has offered intriguing explanations for the peculiar behavior of dwarf galaxies, particularly those orbiting the Milky Way and Andromeda. Many of these small galaxies appear to be aligned in planes and exhibit correlated motions, suggesting a common origin, perhaps from a tidal interaction with a larger galaxy. If these are indeed tidal dwarf galaxies, formed from ejected baryonic material, they would be expected to be devoid of dark matter according to the standard model. Yet, they still exhibit mass discrepancies perfectly in line with MOND's predictions. Even the phenomenon of gravitational lensing, where the path of light is bent by massive objects, has shown some surprising alignment with MOND. While traditionally seen as a strong proof for dark matter, weak gravitational lensing around isolated spiral and elliptical galaxies has been found to be consistent with Milgrom's law, demonstrating that the gravitational field extends flatly out to vast distances, exactly as MOND predicts. Strong gravitational lensing events, like those producing Einstein rings, also align with the mass discrepancy acceleration relation that is characteristic of MOND. Consider also the stability of disk galaxies. Both MOND and dark matter halos contribute to stabilizing these delicate structures, preventing them from collapsing into more elliptical shapes. MOND predicts that this added stability only applies to regions of galaxies within the deep MOND regime, where accelerations are below a. This suggests that spirals whose central regions have accelerations greater than a might be less stable and thus less likely to survive to the present day. This could explain the observed Freeman limit on the central surface mass density of spiral galaxies, a natural outcome in MOND that requires careful fine-tuning in dark matter models. Even galactic bars, those elongated structures of stars found in many spiral galaxies, pose a puzzle for dark matter simulations, appearing too pronounced and rotating too quickly. Yet, MOND-based calculations seem to offer a more natural fit. Recent studies of open star clusters, observing asymmetries in their tidal tails and their lifetimes, also find inconsistencies with Newtonian dynamics, but a surprising consistency with MOND. Perhaps one of the most compelling recent findings came in 2023 from a study that measured the accelerations of over 26,000 wide binary star systems. These are pairs of stars so far apart that their mutual gravitational pull is extremely weak. The study claimed that those binaries with accelerations below a certain threshold systematically deviate from Newtonian dynamics, but align with MOND's predictions. This would be a crucial near-field test of MOND, operating right here in our cosmic backyard. While the results are still debated and require further verification, the mere possibility of testing such a profound theory with such precision in our local galactic neighborhood is thrilling. Furthermore, the early universe itself might be singing a MOND tune. In 2024, a study proposed that the rapid formation and growth of the universe's earliest galaxies, a challenge for the Lambda CDM model, is actually predicted by MOND. These observational successes, particularly those that emerged after Milgrom's initial proposal, have emboldened MOND proponents. They argue that MOND offers a more coherent and parsimonious explanation for a wide range of galactic scale phenomena, often with fewer adjustable parameters than dark matter models. It presents a captivating alternative, suggesting that the missing mass problem isn't about an invisible component of the universe, but about a subtle, yet fundamental, shift in the laws of gravity themselves. It asks us to reconsider what we truly know about the forces that shape the cosmos, urging us to remain open to the possibility that the universe, at its most expansive and most tenuous, operates under rules we are still learning to decipher. We've ventured deep into the intellectual landscape of modified Newtonian dynamics, understanding its foundational principles and its bold challenge to the conventional dark matter paradigm. Now, it's time to examine where MOND truly shines, to explore the surprising victories it has claimed against the current of mainstream astrophysics, and to see how its predictions align with the observed universe in ways that can leave even its skeptics pondering. While MOND was inherently designed to explain the anomalous flatness of galaxy rotation curves, the very problem that ignited the dark matter hypothesis, its success extends far beyond merely matching these observations. Every instance where a galaxy's rotation curve precisely conforms to Milgrom's law, without the need for invisible dark matter halos, adds a profound weight to its empirical validity. It's not just a fit, it's a consistently recurring pattern that MOND elegantly encapsulates. One of the most compelling triumphs for MOND is the baryonic Tully-Fisher relation, or BTFR. This is a fundamental empirical relationship that links a spiral galaxy's total baryonic mass, that's all the ordinary matter we can see, the stars and gas, directly to its asymptotic rotation velocity. Newtonian dynamics, even with dark matter, struggles to predict such a tight, consistent correlation. The dark matter model requires complex fine-tuning of dark matter halos to match the baryonic distribution. But in MOND, this relation emerges naturally, a direct consequence of Milgrom's law in the deep MOND regime. It was a prediction of MOND, known as the mass asymptotic speed relation, long before its observational confirmation through the BTFR solidified its significance. The fact that galaxies so precisely follow this MONDian prediction is a powerful piece of evidence in its favor. Then there's Renzo's rule. This refers to the remarkably tight correlation observed between the features in a galaxy's baryonic mass distribution and the corresponding features in its rotation curve. If dark matter were truly the dominant gravitational component, forming vast, diffuse halos that only loosely follow the visible matter, you wouldn't expect such a precise one-to-one mapping. Yet, MOND predicts this intimate connection, as the gravitational field itself is directly tied to the baryonic mass. Observations of numerous spiral galaxies confirm this tight correlation, presenting a significant hurdle for dark matter models that often struggle to reconcile the smooth, large-scale distribution of dark matter with the intricate details of baryonic structures. Another striking correlation is the mass discrepancy-acceleration relation. MOND predicts a specific acceleration-dependent relationship between the observed gravitational acceleration of a star within a galaxy and the amount of missing mass that would be inferred by Newtonian analysis. Crucially, MOND predicts that this inferred dark matter mass effectively vanishes when the star's centripetal acceleration exceeds the critical value, a zero, where MOND reverts to Newtonian mechanics. From a dark matter perspective, it's incredibly challenging to explain why the amount of unseen mass should correlate so precisely with the observed acceleration, or why there should be a fundamental critical acceleration scale above which dark matter suddenly seems unnecessary. This precise relationship, borne out in observational data, stands as a testament to MOND's predictive power. Consider also the behavior of particularly massive galaxies, especially large ellipticals. These galaxies often operate within the Newtonian regime, where accelerations are greater than a zero, out to very large radii, encompassing most of their baryonic mass. In these regions, MOND predicts that their rotation curves should, in accordance with Kepler's laws, fall off as 1 over r. The dark matter hypothesis, conversely, would typically expect a significant boost from a massive halo, leading to a flattening of the rotation curve, even in these systems. Observations of these high-mass ellipticals, however, tend to bear out the MOND prediction, showing a more Keplerian decline where MOND suggests they should. In a compelling study published in 2020, astronomers analyzing data from the Spitzer Photometry and Accurate Rotation Curves, or SPARC, sample, combined with estimates of the large-scale external gravitational field from an all-sky galaxy catalog, found highly statistically significant evidence for violations of the strong equivalence principle in weak gravitational fields around rotationally supported galaxies. What they observed was entirely consistent with MOND's external field effect, which we discussed previously, and notably inconsistent with tidal effects as predicted by the lambda CDM model. This was a direct test of a unique MOND prediction, and the results leaned heavily in MOND's favor. More recently, in 2023, a study further asserted that cold dark matter models struggle to explain galactic rotation curves, while MOND consistently succeeds. Beyond spiral galaxies, MOND also offers intriguing insights into the enigmatic world of dwarf galaxies. Recent observations have revealed that many dwarf galaxies orbiting the Milky Way and Andromeda are not randomly distributed, but rather lie preferentially in a single plane and exhibit correlated motions. This planar alignment strongly suggests that they may have formed during close encounters with other, larger galaxies, essentially as tidal dwarf galaxies. If this is the case, the presence of mass discrepancies within these systems provides strong support for MOND. Tidal dwarf galaxies, by their very formation mechanism, are expected to be nearly devoid of dark matter. Yet, observations indicate they possess mass discrepancies consistent with MOND's prediction that all isolated, gravitationally bound objects in equilibrium, with accelerations below a0, should exhibit such discrepancies when analyzed with Newtonian mechanics, and should fall on the baryonic-Tully-Fisher relation. 3 objects definitively identified as tidal dwarf galaxies indeed show mass discrepancies that align perfectly with MOND's predictions. Furthermore, a 2022 survey of dwarf galaxies in the Fornax cluster concluded that the observed deformations of these dwarfs and the absence of low surface brightness dwarfs toward the cluster center are incompatible with lambda CDM expectations, but well consistent with MOND. These are complex dynamics, and MOND's ability to explain them without invoking dark matter is a powerful argument. Gravitational lensing, the bending of light by massive objects, offers another arena for testing these theories. While the early relativistic generalizations of MOND, like Tevis, initially faced challenges with lensing observations, more recent analyses of weak gravitational lensing around isolated spiral and elliptical galaxies show that the gravitational fields of these galaxies follow Milgrom's law out to distances of up to a megaparsec. This is precisely what MOND predicts for systems that exhibit flat rotation curves. Even strong gravitational lensing events, like Einstein rings, appear to confirm the MOND expectation for the mass discrepancy acceleration relation, further bolstering its observational foothold. But the successes don't stop there. MOND also provides elegant explanations for phenomena that are puzzling in the dark matter framework. For instance, both MOND and dark matter halos are believed to stabilize disk galaxies, preventing them from collapsing or transforming into elliptical galaxies. However, in MOND, this added stability is only available for regions of galaxies within the deep MOND regime, where accelerations are below a0. This implies that spiral galaxies with accelerations above a0 in their central regions should be more prone to instabilities and thus less likely to survive over cosmic timescales. This could explain the puzzling Freeman limit to the observed central surface mass density of spiral galaxies, a limit that roughly corresponds to a0 over g. In dark matter-based galaxy formation models, this scale must be introduced by hand, lacking a fundamental explanation. MOND, on the other hand, provides a natural, intrinsic reason. The rotation of galactic bars within barred galaxies also presents a challenge for dark matter simulations, as they often predict bars that are too pronounced and rotate too quickly compared to observations. MOND-based calculations, however, seem to match these observed characteristics more closely. In 2022, research into open star clusters argued that asymmetries observed in the population of leading and trailing tidal tails and the overall lifetime of these clusters are inconsistent with Newtonian dynamics but consistent with MOND. These are subtle, detailed dynamics that point towards the influence of Milgrom's law. Perhaps one of the most intriguing and hotly debated recent findings came in 2023, when a study measured the acceleration of over 26,000 wide binary star systems within 200 parsecs of Earth. This study claimed to show that binaries with accelerations less than 1 nanometer per second squared, a realm of extremely low acceleration, systematically deviate from Newtonian dynamics, yet conform remarkably well to MOND predictions, specifically those of the Ackwell formulation. While these results are currently under scrutiny and dispute, with some arguing about the quality controls, the original authors maintain that their findings hold even with additional rigorous checks. If confirmed, this would represent the first direct laboratory scale, or at least local, evidence for MOND's predictions within our cosmic neighborhood. And finally, looking to the distant universe, a 2024 study suggested that the universe's earliest galaxies formed and grew with a rapidity that is difficult for the lambda-CDM model to explain. However, such rapid growth is precisely what MOND predicts, offering a potential solution to a growing cosmological puzzle. These observational successes, spanning from the delicate structures of dwarf galaxies to the fundamental properties of galactic rotation, and even potentially within our own stellar neighborhood, represent a powerful accumulation of evidence for modified Newtonian dynamics. They demonstrate MOND's ability to not only address the missing mass problem, but to also make unique predictions that have been subsequently observed, often presenting significant challenges for the prevailing dark matter paradigm. However, as compelling as these victories are, MOND, like any scientific theory, is not without its own set of formidable challenges, which we will explore in our next segment as we confront the areas where MOND struggles against the vast complexities of the cosmos. While MOND offers compelling solutions for galactic rotation curves and other phenomena at the local scale, it's not without its profound challenges. As we venture beyond the comforting embrace of individual galaxies and expand our gaze to the grand tapestry of the cosmos, the neat explanations MOND provides begin to fray at the edges. One of the most formidable hurdles MOND faces lies in the acoustic peaks of the cosmic microwave background. Imagine the early universe, a dense, hot plasma, where sound waves rippled through the primordial soup. These ripples, these ancient echoes, left their indelible mark on the cosmic microwave background, the faint afterglow of the Big Bang. They reveal a very specific pattern of peaks and troughs, a signature that the standard cosmological model, lambda-CDM, with its dark matter and dark energy, has been remarkably successful at explaining. This model predicts the precise amplitudes and locations of these peaks, like a cosmic tuning fork resonating with the universe's initial conditions. However, MOND, in its original formulation, struggles to reproduce these observations with the same fidelity. Without the added gravitational influence of dark matter, the dynamics of the early universe, and therefore the propagation of these cosmic sound waves, would be fundamentally different. Reconciling MOND with the finely tuned structure of the cosmic microwave background remains a significant theoretical puzzle, requiring substantial and often intricate modifications that detract from the theory's initial elegance. Beyond the cosmic microwave background, MOND also encounters difficulties when confronted with the large-scale structure of the universe. Imagine the universe as a vast cosmic web, woven from colossal filaments of galaxies and immense, empty voids. The distribution of matter on these gargantuan scales, The way galaxies cluster together and form these intricate structures is also exquisitely sensitive to the overall gravitational dynamics. Lambda CDM provides a coherent framework for how these structures grew from tiny quantum fluctuations in the early universe, guided by the gravitational hand of dark matter. MOND, by modifying gravity at low accelerations, would alter this growth process. While it might explain the internal dynamics of individual galaxies, extending its principles to the vast scales of the cosmic web often leads to predictions that don't quite align with what our telescopes observe. The matter-power spectrum, which quantifies how much structure exists at different scales, presents another significant discrepancy for MOND. Then there's the realm of relativistic effects. Remember, MOND was initially conceived as a modification of Newton's laws, which are classical, non-relativistic. But the universe is a place where Einstein's general relativity reigns supreme, particularly when dealing with strong gravitational fields, vast distances, and the fabric of spacetime itself. Phenomena like gravitational lensing, where the immense gravity of massive objects bends the path of light, and the recently detected gravitational waves, ripples in spacetime caused by accelerating masses, are purely relativistic effects. An original, non-relativistic MOND theory, by its very nature, cannot directly explain these phenomena. To address this, physicists have sought to develop relativistic generalizations of MOND. One prominent attempt was TeVis, or tensor vector scalar gravity, developed by Jacob Bekenstein in 2004. TeVis aimed to embed MOND behavior within a relativistic framework. While it showed some promise in explaining gravitational lensing, it introduced its own set of complexities, requiring multiple extra fields and struggling to fully align with observations of the cosmic microwave background and other relativistic phenomena. Moreover, the recent direct detection of gravitational waves by LIGO and their measured speed, indistinguishable from the speed of light, has posed a serious challenge to many modified gravity theories, including some versions of TeVis, which predicted different propagation speeds for these cosmic ripples. But perhaps the most glaring and persistent problem for MOND, the one that proponents of dark matter often point to as a fatal flaw, lies in the heart of galaxy clusters. These titanic congregations of hundreds or even thousands of galaxies are the largest gravitationally bound structures in the universe. When analyzed using MOND, these clusters still exhibit a residual mass discrepancy. Even after accounting for Milgrom's modifications, there appears to be more gravitational pull than can be explained by the visible baryonic matter alone. This is the cluster conundrum. While the amount of missing mass in a MOND analysis is significantly reduced compared to a purely Newtonian one, sometimes by as much as 4/5, it doesn't entirely vanish. This implies that even if MOND is correct, there might still be some form of unseen matter at play within these colossal structures, or perhaps MOND's applicability diminishes at these truly enormous scales. Some physicists have speculated that perhaps massive, but still unknown, neutrinos, weighing around 2 electron volts, could account for this residual mass in galaxy clusters, a workaround that attempts to preserve MOND successes at the galactic level. The most famous example, and a crucial test case for both MOND and dark matter, is the bullet cluster. This magnificent cosmic collision involves 2 galaxy clusters that have passed through each other. Observations of the bullet cluster using X-ray telescopes reveal the hot gas, which makes up the vast majority of the normal baryonic matter in the clusters. This gas, being collisional, slowed down during the impact and remains concentrated in the center of the collision. Meanwhile, gravitational lensing observations, which map the distribution of mass, reveal 2 distinct peaks of gravitational potential that are offset from the X-ray gas, aligning instead with the paths of the individual galaxies that largely pass through each other without significant interaction. In the lambda CDM model, this is a straightforward explanation. The dark matter, being collisionless, would have passed through almost unimpeded along with the galaxies, creating the observed gravitational peaks, while the normal gas slowed down. This offset between the visible baryonic matter, the X-ray gas, and the gravitational potential, mapped by lensing, was hailed by many as a direct empirical proof of dark matter's existence. For MOND, the bullet cluster presents a much more complicated picture. While proponents of MOND have shown that the theory can reproduce some aspects of the bullet cluster's offset, by predicting that the effective missing mass would be centered on regions of low acceleration, which correspond to the galaxies themselves, it still struggles to fully explain the entire phenomenon. The residual mass discrepancies, even after applying MOND, persist in several core regions of the bullet cluster, undermining its complete explanatory power for such a critical observation. These deep chasms in MOND's explanatory power, particularly on cosmological scales and within massive galaxy clusters, mean that it has not gained widespread acceptance within the broader scientific community. While it offers a seductive elegance for individual galaxies, the universe at large seems to demand something more, something perhaps more akin to the unseen, yet pervasive influence of dark matter. The scientific journey, however, is rarely a straight line, and these challenges merely define the next frontiers of exploration. Our cosmic journey through the mysteries of missing mass has brought us to a crossroads. We've explored the prevailing paradigm of dark matter and delved into the radical alternative presented by modified Newtonian dynamics. Both offer compelling explanations, yet both face their own profound challenges. As we stand on the precipice of discovery, the grand debate continues to shape the future frontiers of our quest for cosmic truth. The journey to understand the universe is, by its very nature, a process of refinement, challenge, and paradigm shifts. The tension between the lambda-CDM model and MOND isn't merely a scientific squabble. It's a testament to the scientific method in action, a constant striving for better, more comprehensive explanations. It forces both camps to sharpen their arguments, seek new evidence, and confront their limitations. One of the most promising avenues for distinguishing between these two grand narratives lies in the relentless pursuit of observational and experimental validation. Imagine, for a moment, the revolutionary impact of detecting the elusive dark matter particle. Such a discovery, even a hint of its existence, would be a monumental triumph for the lambda-CDM model, strongly suggesting that Newton's laws of gravity, as currently understood, require no fundamental modification. It would confirm the existence of a new form of matter, a silent architect of the cosmos, weaving its gravitational influence across unimaginable scales. Particle physics experiments, deep underground in shielded laboratories, are tirelessly searching for these weakly interacting massive particles, or WIMPs, as they are sometimes called. A definitive detection would undoubtedly reshape our understanding of the universe almost overnight. Conversely, if modified Newtonian dynamics is indeed a modification of inertia, it predicts subtle, yet detectable, anomalous accelerations right here on Earth. These deviations, though minuscule, would manifest at specific times and places throughout the year. Imagine precision experiments, meticulously designed to detect these faint whispers of cosmic influence. Such a discovery, if confirmed, would fundamentally alter our understanding of how forces operate, not just in the distant cosmos, but in the very fabric of reality around us. However, it's crucial to remember that this particular prediction hinges on MOND being a theory of modified inertia. If it's a modification of gravity, as many MOND proponents now lean, then the external field effect caused by Earth's own immense gravitational pull would likely mask these local Ondian effects at our planet's surface. The solar system, our immediate cosmic neighborhood, also presents a unique testing ground. While the gravitational fields here are overwhelmingly strong, far exceeding the critical acceleration scale A0, the precision of our measurements is truly extraordinary. Missions like LISA Pathfinder, launched in 2015, were designed to detect minute gravitational perturbations. Could these missions, or their successors, uncover the anomalous tidal stresses predicted by MOND to exist at the Earth-Sun saddle point of the Newtonian gravitational potential? This region, a delicate balance of gravitational forces, could be a sensitive probe for the subtle Indian deviations. Further, dedicated spacecraft, or even more precise measurements of the perihelion precession of our own planets, could provide crucial evidence. These are not easy experiments, demanding engineering marvels and years of dedicated observation, but the potential rewards are immense. Beyond our solar system, the universe itself offers a vast laboratory. One particularly insightful astrophysical test would involve comparing isolated galaxies with those that are deeply embedded within strong external gravitational fields. If MOND is correct, the internal dynamics of these systems should differ in ways that the standard dark matter model would not predict. The external field effect is a unique MOND signature, suggesting that the dynamics of a subsystem are not entirely decoupled from the larger cosmic environment it inhabits. Observing this effect, or its absence, in diverse galactic environments could provide a powerful discriminator. Another fascinating possibility lies in the study of binary star systems. Imagine two stars, gravitationally bound, but separated by such vast distances that their mutual accelerations fall below the A0 threshold. In such systems, MOND would predict deviations from classical Newtonian mechanics. The meticulous tracking of their orbits, the subtle shifts in their positions over long periods, could reveal the telltale signs of modified gravity in action. This is a challenge, as such wide binaries are often faint and difficult to observe with the necessary precision, but the potential to directly witness MOND's influence on stellar dynamics is incredibly compelling. The redshift dependence of radial acceleration also offers a unique window into these theories. Researchers like Sabine Hassenfelder and Tobias Mistiel have proposed models, such as covariant emergent gravity, that predict a much smaller redshift dependence in MOND scenarios compared to particle dark matter models. As our telescopes become ever more powerful, enabling more precise measurements of radial acceleration across cosmic time, we may be able to discern these subtle differences and finally distinguish between the contenders. The cosmological front also continues to be a battleground of ideas. The lambda CDM model, with its dark matter and dark energy components, has a remarkable track record in explaining the cosmic microwave background, the afterglow of the Big Bang, and the large-scale structure of the universe. The acoustic peaks in the CMB's angular power spectrum are often cited as strong evidence for dark matter's presence, shaping the early universe. MOND, in its original formulation, struggled immensely to reconcile with these observations. While newer relativistic generalizations of MOND have emerged, attempting to incorporate terms that can fit the CMB data, these often come at the cost of elegance, requiring numerous ad hoc additions that diminish the inherent simplicity of Milgrom's original idea. Furthermore, explaining gravitational lensing and the formation of large-scale structures within these modified MOND cosmologies remains a significant hurdle. However, recent observational surprises are also adding intriguing new dimensions to the debate. Some galaxy surveys, for instance, seem to indicate that massive galaxies formed and grew at much greater rapidity in the early universe than is readily explained by the lambda CDM model. MOND, in some of its interpretations, might actually predict such rapid growth, offering a potential advantage in this particular arena. This highlights the dynamic nature of science, new data constantly challenging existing frameworks and opening doors for alternative explanations. And then there's the profound, almost poetic connection that Milgrom himself highlighted. The numerical proximity of his acceleration constant A0 to fundamental cosmological parameters. It's roughly within an order of magnitude of CH0, where C is the speed of light and H0 is the Hubble constant, a measure of the universe's present-day expansion rate. It's also remarkably close to the acceleration rate of the universe due to the cosmological constant, lambda. Is this a mere cosmic coincidence, or does it hint at a deeper, fundamental link between local galactic dynamics and the large-scale evolution of the universe? Could it be that MOND is not just a fix for galaxy rotation curves, but a manifestation of a cosmic principle, perhaps even a hint towards Mach's principle, suggesting that local dynamics are profoundly influenced by the universe at large. Some recent work, exploring a transactional formulation of entropic gravity, even suggests a natural connection between A0, the Hubble constant, and the cosmological constant, weaving these seemingly disparate concepts into a unified tapestry. Ultimately, the grand debate between dark matter and MOND isn't about one theory being inherently right and the other wrong. It's about a scientific journey, a continuous dialogue between observation, theory, and experiment. Both paradigms have pushed the boundaries of our understanding, revealing profound insights into the universe's mechanics. The challenges they face are not roadblocks, but rather signposts guiding us towards new discoveries, forcing us to ask deeper, more fundamental questions about the nature of gravity, the composition of the cosmos, and our place within it. As we continue to build ever more sensitive instruments, as our theoretical frameworks become more sophisticated, and as our curiosity remains unyielding, the universe will undoubtedly reveal its secrets, one profound discovery at a time. Whether the solution lies in the enigmatic embrace of dark matter or in a revolutionary reimagining of gravity itself, the future frontiers of cosmic truth promise to be as awe-inspiring as the universe itself. And we, as curious observers, will be there to witness it all unfold. And so, our grand tour through the revolutionary ideas of modified Newtonian dynamics comes to a close. We've journeyed from the perplexing rotation of galaxies to the subtle shifts in our own solar system, challenged established paradigms, and glimpsed the audacious frontiers of scientific thought. The universe, in its infinite wisdom, continues to hold its secrets close, inviting us to question, to explore, and to imagine. Whether MOND proves to be the ultimate answer, or simply a signpost on a longer road, it reminds us of the incredible human endeavor to comprehend the cosmos. Thank you for sharing this profound exploration with me. If this journey ignited a spark of curiosity within you, please consider liking this video, sharing it with someone who loves to ponder the universe, and subscribing for more deep dives into the scientific unknown. I'd love to hear your thoughts in the comments below. What resonated with you most tonight? And what cosmic mysteries would you like us to unravel next? Until our next shared moment beneath the stars, keep looking up and keep vibing with science.